Alright, I am here and ready to begin. Let me wind this down a bit. Welcome back to Chem 161. Today we are going to finish Chapter 2, hopefully, or at least get real close. Let's see, agenda items. Lab worksheet number 1. Tonight is the deadline, so the due date was yesterday. This is the 24-hour grace period. The assignment closes tonight. Get your assignment in by the deadline. Note that I'm not going to really be available much tonight, so if you have questions, I have like 20 minutes after class that I can try and address them. So get those in on the Discord, and I can help you. I saw lots of people working on the Discord, and that is fantastic. I saw people sharing screens, which is good. Like, I'm going to assume that you're not going to just copy off of each other's screens, because I would notice. Like, this isn't my first rodeo. But, like, I equate that to, like, you sitting next to somebody in the computer lab. So, like, don't feel bad about sharing your screens. Like, I think it's great that people were using the channel voice chat. Because as much as I advocate, like, please use those channels, very few people often do. And having a study session like that, I think, is a fantastic use of it. So good job. I hope that you were able to get a lot of work done. I know a few students asked me questions about sig figs, so I hopefully answered those questions. But yeah, keep up the good work, and definitely use those resources as you did. Like, you don't have to hide it. Like, I was actually going to jump in the voice chat at one point and say, like, hey, is everybody doing all right? But I didn't do that because I didn't want to scare you. Like, why is the professor here? Ah! So, like, if you want me to do that, you can invite me. And I'm happy to do that. But I'm not gonna jump in unannounced, because I feel like that's like, what if you were talking bad things about me and then I interrupted you? Like, I would feel bad. And then you would feel bad, right? So, no. Anyway, what we're going to do today... Oh, sorry, quiz number 1 is due tonight, too. So, make sure that you get quiz number 1 done, although if you don't finish it tonight, it closes tomorrow, so you do have an extra day. Ooh, I need a drink of water. Hold on. Oh, now I have hiccups. Great. Sorry, seltzer water does this to me. On Tuesday, we talked about mass spec, and I gave you the gist of, like, what happens. So we're accelerating particles through this magnetic field. And because we've ionized them, they bend through the magnetic field. And depending on their mass, they will bend and hit the detector. Sorry. I drank that too quickly, I think. So using this device and controlling the voltage for the magnetic field extremely precisely, we can get a very good idea of what the mass of individual isotopes are. Now, what we didn't do is we didn't talk about what the output looks like. And the output looks like this. What this graph prints is, on the y-axis, is just an intensity. So I have made this relative abundance as a percentage. And so what the computer in the mass spec has done, by me telling the y-axis to be, okay, your relative abundance, is it has said, okay, I'm going to integrate across all masses. I'm going to assume that everything I see is 100%. And then I'm going to see how many counts did I get. So at mass 90, I got about 50% of the counts right here. At mass 91, I got just over 10%, and so on and so forth. At mass 93, I saw nothing. At mass 95, I saw nothing. At mass 96, I did see something, and it wasn't just noise. It was like 3% of the counts, and so on and so forth. So this is what a mass spec does, is it looks at the mass of the object that hit the detector, and then it plots that against how many times it saw that happen. If I put in a random sample and 10% of that sample is, like, say, zirconium 91, then 10% of the counts that hit the detector at that mass are going to be zirconium 91. Now, interestingly, you'll notice that the x-axis here is not just labeled mass. It's labeled this thing, whatever this is, mass to charge ratio. And you'll sometimes see this labeled as M divided by Z. And what this is saying is that this is the mass divided by whatever charge was present. So if the mass of my zirconium-90, for example, which is roughly 90 AMU, and I had knocked one electron off of it so that the charge of this was +1, then this would show up at 90 on the chart. However, if I did this and I knocked off 2 electrons on accident, so its charge was +2, it would actually bend twice as far on the magnet, right? Because something that has a charge of 2+ would be attracted to the magnetic field much more strongly than something with a charge of 1+, right? It would be deflected much more strong, in a much more curved line. So the conclusion that we would draw is that, okay, well, this will hit the detector much earlier. And in fact, the number that it would show up at is 45. So if you are doing a mass spec, which you won't at Everett Community College, because we don't have one, unfortunately, that works. But if you go to, like, say, UW for your transfer, UW definitely has a mass spec, because that was literally all I did at UW was mass spec. That was my master's degree, was mass spec, which is why I talk about it, because when you spend 5 years doing something, it never really goes away, and you sort of think back on it with somewhat fondness. I don't know. I enjoyed my time sitting at this stupid little device, stabbing it with a needle and then injecting it with my sample, and then sitting there for 20 minutes while it ran through this spiraling column. But you get an output that looks like this, but you may also get data around half as much as you would expect to. And the reason that it's half is because of this. So the reason that it's called the mass to charge ratio is because in your mass spec, if I go back to this previous thing here, right here in this part where I ionize my sample, where's my pen? There it is. So right in here, I might ionize the sample twice. And if I do, I'm going to get the divided by 2 thing. I might even ionize it 3 times, and then I'd get it divided by 3. But it's increasingly more and more rare to see things that are ionized more than once. So on your spectra, we write mass to charge ratio just to let you know that, because if you have peaks at 90, 91, 92, you're also going to see peaks at 45, 45.5, 46, and so on. And they're going to be really tiny. And the reason for that is, oh, you bumped off 2 electrons instead of 1. So that's why this is labeled as such. So just in case you see these on, say, a quiz or whatever, and you see the words mass to charge ratio, and you're like, what the hell does that mean? That's just what that means. I am only showing you the highest part of it, though. So this is just a spectrum that plots out abundance versus mass. And so you could say, okay, I have 52% zirconium-90, and I know what its mass is, because this would tell you, instead of just saying 90, it would say 90.0889 or whatever. And so from a mass spec, you could calculate the atomic mass on the periodic table. So that's cool and all. So let's suppose that you have done that. I'm going to give you magnesium. What I want you to do is I want you to tell me the mass of magnesium that I should write on the on the periodic table for its atomic mass based on this data. And yes, it is going to give you what's actually on the table for magnesium. You should get 24.3 something. Okay, so do the calculation to ensure that you get that. And then what I want you to do is I want you to make a diagram. I want you to draw what this would look like as the output of the mass spec chromatograph. Okay, so sketch out a graph, make sure you label the axes appropriately, draw the peaks the correct height, and put them in the right spot. And then you don't have to put that in ASCII or whatever in the chat. I will draw that for you when we're done. But do let me know when you're finished. I'll give you like 5 or 6 minutes, and then we'll go over the answer. One more minute, we'll go over the answers. All right, let's go over here. I was trying to draw the chart out, and then I ran out of time here. So give me a second here. I can't write sideways, so what I'm going to do is I'm just going to cheat. So we're just going to do this, and then I'll just tell it, yeah, just take what I selected and rotate it. There you go. No work required. All right, so here's our graph. But first, what we need to do is we need to figure out the average mass using our calculations. So we did, last week, we had the calculation that the weighted average, that's not the pen, there we go. So the average mass was equal to the percentage of the first isotope, so that'd be magnesium-24, times the mass of magnesium-24. Oh my goodness, it's still doing this stupid thing. I thought I had fixed this. So when I write on here, it's sometimes just, it's doing this with my pen, and I hate it. And I don't know what's causing it. Plus percent of 25 times the mass of 25. And then we'll do that for 26. And so that's going to be, so the first one is 0.7899 times 23.985 AMU plus 0.1000 times 24.983 AMU plus 0.1101 times 25.983 AMU. And you should get 24.305, but I'm going to type in the calculator just to see. All right, so for sig figs, I believe that we go to the, so we probably go to 2 decimal places here. 3, 0. I did this all in one calculation, but I believe that this number right here, this should be 4 sig figs times 23.985, which will give me a number with 2 decimal places. So when I add them all together, it should have 2 decimal places. And now we need to draw this on the chart. So what I'm going to do is I'm going to say, okay, so I'm going to go 22, 23, 24, 25, 26, 27. And then we're just going to make lines that reflect this. So at magnesium 24, which is about 23.95, we're going to go up. I don't know. We'll just do that. So we'll say 100, 50. There we go. So we should get one peak at 24 that looks like that. And then at 25, we'll get a peak that looks kind of like this for 10. And then at 26, we'll get a peak that looks like that for 11. So that's what your chart should look like, something like that. All right, that's mass spec. That's all there is to it. Literally spent 3 to 4 years just doing mass spec on random stuff in NMR, which you'll learn about in 163. So there you go. That's all there is to it. Now you two can have a master's. I mean, there's more to it than that. There's a bunch of things you could do with it, but it's meant to be a tool. All right. So the last bit of chapter 2 is going to be calculations that involve the mole. It's going to be stuff that about drawing formulas and things out. I think the first slide is just a bunch of pictures of different molecules here, so let's get that going here. Yeah, there you go. So you're going to see in Chem 161 all of these methods of drawing things used. Now, some of these are going to be more meaningful to us than others, and we're going to talk about all of them more or less in Chapter 4 is going to be where we're going to hit all of these. So, the first one that you see here is the molecular formula. This is just how we write molecules out. We are not going to use this for any structural identification. We're going to just use this as a convenient way to type out or write out what is contained in a molecule. Now, this class we're going to talk a lot about bonding in chapters, late chapter 3 and then all of chapters 4 and 5. We're going to talk about chemical bonding. And when we talk about bonding, we're going to concern ourselves about the orientation of atoms in space, such as what atoms are bonded to what, but also in which direction they are coming off of the atom that they're connected to. So drawing these models out as accurately as possible is going to be very crucial. The first method that we're going to employ is the structural formula. This is the way that you draw Lewis structures, and we drew Lewis structures in 140. We did very elementary ones, where we drew everything at right angles, and that's fine. But in reality, molecules are not flat on pieces of paper. Otherwise, we would all be two-dimensional objects like Paper Mario, right? In reality, things occupy 3 dimensions. And so these other two models, this ball and stick model and the space-filling model, these are drawn with the intent to communicate the 3-dimensional orientation of molecules in space. And so you can kind of see this with this structure here. So right here, this is trying to represent that this is a tetrahedron. And so that line that I drew on the bottom is only touching the white hydrogen atoms and not the carbon atom that is actually in the center of the pyramid. Now, what's the difference between the ball and stick model and the space filling model? The ball and stick model just illustrates the angles of the atoms very effectively. So all the atoms are exaggerated in their distance from the central atom. The space filling model gives you an actual model of how the atoms around the molecule are structured and actually take up space. And the reason that they all look like spheres that are sort of melded together is because the orbitals of the electrons around atoms tend to be spherical in nature. And where those spheres overlap is where bonding occurs. We're going to go into that in great detail in chapters 4 and 5. Now, the drawback against the space-filling model is that it kind of obscures bonding. For example, if you look down here at the sulfur S8 molecule, this structure on the right, it's a little less clear where the atoms are oriented in space, like what the angles are, and the ball and stick model over here makes that much more clear. The drawing of the Lewis structure completely obscures it, though. You would have no idea that this was in 3 dimensions based on this octagon of sulfurs that we just drew in a ring. So, different models will be used for different purposes, and our job is to employ the correct one to fulfill our need. If we're talking about structure and we want to know what the bond angles are, the middle one is the best one. Is molecular geometry something we're going over this quarter? Yeah, that's chapter 4 and 5. We're going to talk all about shapes. In fact, I'm going to give you mole view. I mean, I could just give you mole view right now if you want to play with it, since we're going to be getting to that in a few weeks here. So let me get mole view up here. I'll just paste the link in the chat here for you. So we're going to be using this program as our modeling kit. I unfortunately do not have a modeling kit to give you, nor do I have one at home that I can point my webcam at so you can see me modeling stuff. But I do have mole view, and mole view is a really helpful molecular modeler that you can just draw any Lewis structure you want to in the left side of the panel, and then it spits out the three-dimensional shape of it in the right side. I believe the default molecule it gives you when you load this up is caffeine. So this is what caffeine looks like in 3 dimensions. So you can see it is mostly flat, except for the CH3 groups coming off the side, which are 3-dimensional and kind of poke out of the plane. If you haven't clicked on that, I guess I could capture it, huh? Yeah, let's put mole view on the screen. So there we go. So you could spin this around, and you can see that this molecule is not flat. There's stuff coming up and down on the molecule, but it looks kind of flat on paper. And over here on this diagram, it totally does look flat. And I can edit this. You can do whatever you want to with this. So I could just add extra stuff to it. So if I add this over here and then I click this button, it will re-render it. There you go. And so over here, this is the thing that I added to it. So this is not caffeine anymore. This is now like tert butyl caffeine or something. I don't know. Anyway, so that is there if you want to play with it. And we're going to play with it in chapter 4. When we're representing molecules on paper, it's very important that you convey the intended meaning. If you say H2, and what you actually meant was 2 independent hydrogen atoms, then you said the wrong thing. So H2 is a molecule. The 2 in the front indicates a quantity. So quantity. The 2 as a subscript represents the number in a molecule. So be very careful about your intent when you are typing in stuff. Don't write 2H if you intended to write H2 and vice versa. So very important that we don't confuse that, because this is already confusing enough, right? All right. So let's do... Oh, I thought we were doing calculations. I guess we have this last slide here. There are several molecules in nature that exist as diatomic pairs. And those 7 are shown on the screen here. I call them the silly 7. I don't know if this is well known. I swear I was told this in high school, and then I've never found it online again. I mean, Google might help a little bit for this, but I swear I've looked and it hasn't come up yet. But the 7 diatomic elements are these 6 over on the right that form the shape of a 7. So it's these guys right here. And the stem of the 7 is in group 7A, or 17. And then hydrogen is over here by itself because he's silly. So that's why they're the silly 7. all of these find another element or atom of that element and then pair up. So you won't find N by itself in the atmosphere. Nitrogen, monoatomic nitrogen is exceptionally rare. It will always find another nitrogen atom and go boop and just bond. Same with oxygen. Oxygen atom by itself is pretty rare. It's a lot less rare than nitrogen by itself, though. And there's a reason for that. And again, we'll talk about that in chapter 4. Same with the other guys in group 7A here. They all pair up. Now note that we are talking about neutral atoms here. We are not talking about something like Cl-. Cl- is incredibly common. Cl by itself with no charge, though, is very, very reactive and would immediately either oxidize something to become Cl-, or it would pair up with another Cl and become Cl2. Again, more of that in chapter 4. All right. In 140, we talked about empirical formulas. The empirical formula of a molecule is its simplest ratio. So, for instance, if I had benzene here, and I were to split my benzene into carbons and hydrogens and then throw all of the pieces that matched in a bin, what I would observe is not a random errant pen stroke here. What I would observe is the following. If I had a bin for carbon and a bin for hydrogen, and I put some undetermined number of benzenes in the detector, I would notice that this is what I get. I would get roughly the same amount. And so I would say that the ratio of carbon to hydrogen here is 1:1. And so I would say that the empirical formula is just that, C1H1, or CH. Because this is the simplest ratio of the atoms. And the reason that that's helpful to us is because most of the time we cannot look at individual molecules. In fact, it's like nearly all of the time. If I throw a sample of benzene into a device that like atomizes it, it rips apart all the bonds because I heat it to like 5,000 degrees Celsius or whatever. And then I just collect all of the atoms individually and weigh them. So like maybe I have a trap that specifically absorbs carbon when it passes through it, and so that I could then weigh the trap afterward to see, oh, okay, I have this much carbon in the carbon trap. How much hydrogen do I have? Well, I would have whatever the difference was in mass or something like that. And from there, I could count a number of atoms. I would have some error with that measurement because I can't ever count discrete individual atoms. So I'd have trillions of atoms or whatever. And I would realize that, yeah, the numbers are roughly the same. So I would say, okay, the empirical formula is 1:1, but I know nothing about how many were in the molecules because that information was lost when I did the analysis. If I rip apart all the bonds, I don't know how many were bonded together. I just know that in my sample, I had the same amount of carbons that I did hydrogen. So doing this sort of analysis will get you what's called the empirical formula. And that can be helpful for calculations that we're going to do in 162 when we do stoichiometry and stuff like that. All right. So I want you to tell me the empirical formula for glucose here. If you were to rip apart all the bonds and stack all the matching things, what would you notice the ratio of atoms was? And you can do this just from the coefficients. Divide out the biggest common multiple that you can find in all of those. Now I'm thinking about it, I guess it'd be a factor, right? The biggest common factor. All right, very good. So it is CH2O. And the way that we get that is we just divide everything here by the biggest common factor that we can put in there. So that'd be 6. So 6 divided by 6 would be 1. 12 divided by 6 would be 2. And 6 divided by 6 is 1. So this would be the empirical formula, CH2O. Good. All right. Now, for CO2, there is no common factor that you can divide out because C is already 1. You can't have fractional atoms, right? So a formula can be its own empirical formula. That is possible. For larger molecules, that happens when you have like an odd number of things. So if I had like C13H12NO2, there's no number I can divide 13 by to get another whole number. So, all right. What are some other funky things that we can do with structures? Isomerism is not going to be something that we really talk about until 261. It's mentioned in your textbook, so I'm going to talk about it here. An isomer is a structure that can be made from a chemical formula. If you have multiple isomers, that means you can get different formulas. Now on the screen here, I have 2 different formula structures, but they all have the same chemical formula, C2H4O2. One of these is used in your cooking. You eat fish with it. The other one is toxic and will kill you. Which is which? Turns out the one on the left, acetic acid, is vinegar. This is safe for consumption. Methylformate, on the other hand, is not. Do not consume. You do not want to eat aldehydes. They are not good for you. And the only difference really here is that I took this CO group and this O right here, and I said, let's just swap. You're going to now be bonded to the CH3. I'm going to be bonded to the H. How's that? Okay, sure. And it's very interesting that by doing that, we can create something that is extremely toxic. The reason for this has to do with geometry, which we're going to talk about in this class. A thing about geometry that we care about is how molecules fit into other things. For example, enzymes. Your body has bunches and bunches of enzymes that are all tailored to do very specific things. And the way that they are tailored to react only with certain molecules is by shape. Only certain shaped molecules will fit in there. Therefore, if something fits, it sits, right? And that must be the thing that it reacts with, or it's a cat. If you get a molecule that has a different shape and it tries to fit in an enzyme, it might fit in some other enzyme that it's not supposed to, and then it can create toxic byproducts. So we're going to care a lot about shape in biology. If you are a biology major, geometry is the most important thing in chemistry for you. So those isomers right here, these are called structural isomers. Structural isomers have a different structure, but they are not the only type of isomer that exists. There's an interesting form of isomer called a geometric isomer. Your textbook calls these spatial isomers, but I'm calling them geometric isomers because in space, they have a different spatial geometry. Now, I have circled a carbon atom here in both of these that is unique depending on the structure that you're looking at. And it's very hard to see this. And so what I'm going to try and do is I'm going to try and get this into mole view here. I can't type it in, or I can't draw it in because it's too complicated and it'll take too much time. But MoleView has these in here. So if I do plus Carvone, and then I do MoleView. So I'm opening up 2 different windows here. So and I do minus Carvone. Okay, so let me see if I can show the difference here. Rotating this around is going to be the challenge here. Come on. Sorry, I'm trying to rotate this off screen so you don't have to watch me just fumble about with this molecule. Okay, so we got that one. All right, are these... Oh, it didn't actually draw the geometry correctly. Oh, wait, maybe it did. Yeah, there we go. Okay. So they are mirrors of each other, but what you're going to see is that they're not the same structure. And I'm trying to get these to be as close to each other as possible. It's very difficult. Very good. Is that better? That's close enough. Okay. So what I'm going to do is I'm going to capture this so that you can see this on the screen. Okay, so here's plus carbon. So this is the structure that's on the left of the thing down there. So let me just do that. So there we go. So this is plus, and so you can see I tried to put the oxygen on the left here, and you'll notice that with my connections, my double bond goes up. But then if I look at minus, here's the difference. So I've got my oxygen still kind of over here on the left, so it's pointed away, but now the double bond points down. And this can't rotate this around because it's stuck in this ring, right? So this is all stuck in place. But you can see the difference here is that this whole back part spins around. And so you get a very interesting, different structure in space that ends up having a reflection, and they aren't actually the same thing. And so there is a feature of molecules called chirality. A molecule is chiral if you have 4 unique things connected to one atom. So this circled atom here is chiral. And what ends up happening is you get a different molecule in space. And you can kind of see that here in this structure. It's very hard to make out, though. You can see that this stuff down here for each of these is not quite the same. So yes, this happens when you have molecules that are mirror images of each other. So for instance, if you look at your hands are a great example of chiral structures. Your hands are mirror images of each other, aren't they? But if you try and rotate your hands such that if you were to place them on top of each other, they would look exactly the same, you cannot do that. Because if you put your thumbs on both sides, then your palms face opposite ways. There's no way for your left hand and your right hand to look exactly the same, with your palms in the correct direction and your thumbs on the same side. Unless you have 2 left hands. Then I literally cannot help you there. So molecules can be like that too. And so spatial isomers are a reflection of that. So these 2 things, caraway and spearmint, are different isomers, and because they have different shapes in space, they fit into your taste receptors differently, and you get a different taste as a result. Spearmint tastes minty fresh. Caraway, to my understanding, tastes like licorice. All right. The last thing that we're going to do in Chapter 2 is we're going to talk about the mole. We've already talked about the mole a lot in 140, so we're going to breeze right through this, but we're going to do that after the break. So when we come back from the break, we will bust out the calculator. We'll do some mole calculations. I don't have the timer up here. Let me get that here. And we'll just put some more Paradise Killer music on for 10 minutes. So we'll see you in a bit. There we go. Just let the music finish up here. Okay. Sorry, I was answering a question for somebody, and it's like, I had to type faster. All right, so let's do some calculations with the mole. So we know what the mole is. The mole is a quantity of things equal to this many things. This number is named after the person who did the calculations and the research to get it, or more appropriately, probably his research team did it, and he was the lead of that, so he got the credit. This is Avogadro's number, 6.022 times 10 to the 23. You probably have this memorized because it is such a unique number, and we use it a lot. By definition, 1 mole of carbon-12 has a mass of 12 grams exactly, and is equal to Avogadro's number of atoms of carbon-12. Now, Avogadro's number is the only inexact thing in here because we can't calculate this all the way down to the infinitesimally small atom. So we have the first 4 digits and then the next, 19 digits or whatever that come after this. I think the next ones are 315 or something, but I don't know. We're only ever going to use 4 digits anyway, so 4 sig figs for Avogadro's number is the best we got. The point is, it is inexact. It is not 6.022000000. All right. For any given element on the periodic table, we have 3 relationships, and that is to just link any 2 parts of those inequality together. Of these relationships, these top 2 are the most important. The third one is, it's nice, it exists, we're going to ignore it. These 2 are the 2 that we care about. If you wanted to go directly from grams to atoms, yeah, you could. We won't do that very much in this class, and then in 162, when we see this stuff again, we won't do it ever again at all. Now, on your periodic table, which I don't know if I still have open from last class. Oh, I do have it open. Here it is. On your periodic table, hold on, periodic table. There we go. Periodic table. You will notice that we have the mass numbers, which we were calculating for any given element. I'm just going to click one. Right here, this number right here. We were calculating mass percentages from isotopic abundances. This is the mass of 1 mole of that element in grams, and you should know that by now. So this is the atomic mass, or also known as the molar mass. So 1 mole of gallium would have a mass of 69.723 grams. Now, we don't know what isotopes are in the mole of gallium. All we know is that it is a mixture based on the percent abundance of different isotopes of gallium that exist naturally. So that's why we're going to be using that number. We're going to be assuming that we are using 1 mole of just generic gallium that is an appropriate mixture that is representative of what we find on Earth. So if, for example, I asked you, hey, what's the molar mass of iron? You would find iron on the periodic table, and there, oops, I gotta click on it again to keep it stuck there. And there it is, 55.845 grams would be equal to 1 mole. How many sig figs should you use for these problems when you're doing molar masses? If you have a periodic table that has a certain number of sig figs, use all of them. Oops, I didn't mean to click on iron. So I would use all 5 of these for this calculation. Generally speaking, using as many as are available is nice. I want you to use at least 4 if you can help it. For some reason, lithium right here only has 3 listed. I think my periodic table, wherever it is, has 4, 6.941, yeah? Yeah. So, not sure why there's only 3 on this periodic table, but anyway. We don't want to limit our precision of our calculation to just 3 sig figs, so at least 4 would be handy. All right, we could do this for compounds. If I wanted the molar mass of sodium chloride, I could go over here and I could say, okay, well, sodium is 22.990. 22.990. I don't know if you could see the calculator. We can't. So we'll do that. And then I could go over here to chlorine and say, chlorine is 35.453. I know what the next number is because I've done this a million times. And then this would be what I report for the molar mass. You're going to do that so many times that you're going to get sick of it. So what we're going to do instead is our favorite website, Lentech. Good old Lentech. Here it is. There's your Lentech. Here's your Lentech. And on Lentech, what we do is we just type in the molar mass and it spits it out. There you go. So don't waste your time calculating molar masses. Like, I trust that you can add two numbers on the periodic table together. What I don't trust is that you won't make a calculator mistake, because I sure won't. Or I sure will, I should say. I make calculation mistakes all the time, and then I look at my work and I'm like, where did my mistake go? And guess what? It's the molar mass. So just typing in your molar mass, so you can do whatever you want to. So like C13H18. N2O5. There you go. That's whatever that is. So, saves you a lot of time. And there's even some random compounds in here like abietic acid. I don't know what this is. That's what it weighs. Now we've learned. How about naphthalene, which is in mothballs, or lysine, which is an amino acid? You can get all those things in there. And that is great and wonderful, and it saves you a lot of time. So just use that. So, all right. Now, from 140, we spent a lot of time doing these types of relationships, converting grams to moles, or converting some number of atoms or molecules or ions or formula units to moles or whatever. So, just as some exercises to show that we know how to do these mole calculations, because we're going to need them in Chapter 6, which is what we're going to start on in a second here. Let's do some practice problems. So, for our first example here, I'm gonna do the example. Ooh, where'd my OBS go? There it is. Moved it to the wrong monitor. Let's do a calculation for how many moles of silver are in this many grams of silver. So, while I'm here, let me go back to this. And we'll put... I already have it captured. Look at that. Okay, so we're just going to go like that. Shove this over here. And then I just have to click on silver. So there we go. Okay, cool. So we should have everything there. So according to the periodic table, 1 mole of silver is equal to 107.87 grams of silver. So let's do dimensional analysis. I have a sample that is 154.1 grams of silver. And I want to turn this from grams into moles. So let's set up those units to do that. Grams of silver, moles of silver. My units cancel out, and then I write the relationship. 1 mole of silver, 107.87 grams. And then we'll just punch it in the calculator. And I get 1.428. So in that sample, there would be that many moles of silver. That's pretty straightforward, right? Was it 1.429? Yeah, I didn't round. Whatever. All right, so I want you to do it. I'm going to make you do another step, though. So I told you how to go from grams to moles. I want you to tell me how to go from atoms to grams. So you know how to turn atoms into moles using Avogadro's number. Similar method, right? Then turn that into grams. So go ahead and try this problem. Type in your answer in the chat, how many atoms there are. And we'll go over the answer in about 4 or so minutes. So see you in a bit. All right, one more minute, we'll go over the answer. All right. So, still have the calculation for the molar mass for silver on the screen. So, I have this many grams of silver. And what I want to do is I want to turn my grams of silver into moles of silver. And then turn that into atoms of silver. I don't know why I was writing S there. There we go. So we can do that. Now, if you did this in one step instead of two, that's fine. You'll get the same answer. So, what's the relationship between moles and grams? 1 mole is however many grams of silver, according to the periodic table. So we got that. And then we'll turn moles into atoms. And in 1 mole of anything, there are Avogadro's number of atoms of that thing. And so, we can do the calculation. 392.5 times Avogadro's number divided by 107.87. And I get this stupidly long number, which I'm going to hit this button. 2.191 times 10 to the 24. All right. So those are some basic calculations that we can do using the mole and grams and so on and so, so on and so forth. All right. Let's do some more complicated examples. So let's suppose that I have butane here. So C4H10. I have 9.213 grams of it. How many molecules are there in this sample? So now you can't just rely upon the periodic table. Now you got to go to Lentech and use that information to go from grams to moles to molecules. So go ahead and do that. I'll give you 3 minutes to do that calculation. Tell me how many molecules are in there. And then we'll do another question based on that answer. All right, one more minute. We'll go over the answer. All right. Oh, I got to go back over here, though. We don't need this anymore. So we'll get rid of that. All right. I do need to get Lentech on the screen, though. That's not what I wanted. There we go. So boop. And then whoop. All right, so we'll put it over here for now. So we need to put in C4H10, which has a mass of 58.12 grams per mole. So we'll keep that in mind for just a bit. But we have 9.213 grams of butane. We want to go from grams of butane to moles of butane to molecules of butane. So we'll do the first conversion, grams to moles. And in 1 mole, there are, and I can't read the number on the preview window here, 58.12. There we go. Grams of C4H10. And then we want to turn that into molecules, so we'll do this. And in 1 mole, there are Avogadro's number of molecules. So how many molecules is that? That it would be 9.213 times Avogadro divided by 58.12, which would be 9.546 times 10 to the 22. All right. So there's that answer. Now, the next question that I have for you is, in this sample of hydrogen or of butane, how many atoms of hydrogen are, oops, sorry, I clicked on the wrong thing. How many atoms of hydrogen are present? So we no longer need this. This can go away. Now, this becomes very trivial to do. You could do this problem on your own if you'd like, but what I can do is I can say in 1 molecule of C4H10, there are 10 hydrogen atoms. So if I just take that number that we just calculated, and I incorporate this into a ratio, I could say in one molecule there are 10 atoms. And so we can do that to figure out how many atoms there are of a piece within the molecule. So just another technique that we can do. I clicked on the wrong thing. There we go. All right. So now I have the practice problems for you to do. Here's the practice set here. So problems 1, 2, and 4 are things that we just did. Problem number 3 is probably my challenge problem. So I could give you an object that is made entirely of a material, and we can link all the concepts we've talked about together. So that's problem number 3. Do problem number 3 last. But these 4 problems are for you to try. How much time do we have left in the class? Oh, we have plenty of time. Okay. So I'm going to give you like 8 minutes to do as many of these as you can. Then we'll just go over all the answers. And then we're done with chapter 2. So here's 1, 2, 3, 4. Go ahead and type in your answers in the chat as you get them. We'll go over these in about 7 or 8 minutes. We'll do our summary, and then we'll start chapter 6, because we'll have a little bit of time to do that today. All right, let's say 2 more minutes and we'll go over the answers here. All right, let's go over the answers here. All right, for number 1, how many moles of helium are in a balloon that contains 19.4 grams of helium? This is a humongous balloon, for what it's worth. All right, so I've got this many grams of helium. We're going to turn that into moles of helium. And according to the periodic table at P table, in 1 mole of helium, there are 4.0026 grams of helium. So we'll punch that in the calculator here. Oops, let's turn this off, though. 19.4 divided by 4.0026. Let's turn that off, equals 4.85 moles of helium. All right, that was the first one. Let's do the second problem. So, the recommended daily allowance of sodium is 2,400 milligrams. All right. How many sodium atoms is that? So first we've got to get from milligrams of sodium to grams of sodium. And a milligram is 10 to the minus 3 grams. And then we can turn that into moles. And a mole of sodium, according to the periodic table, is... Oh, I have it covered up in the window. I'll just use my periodic table. 22.990. There you go. And then finally, we can turn moles of sodium into, what are we trying to do? Atoms of sodium. And in a mole, there are Avogadro's number of atoms. So we'll punch it all in the calculator here. I gotta put that somewhere. We'll just do that. So we got 2,400 milligrams times 1 times 10 to the minus 3 times 1 times Avogadro divided by 22.990. That is a humongous number. Please make that an exponential. There we go. 6.3, actually. 6.3 times 10 to the 22 atoms of sodium. All right, number 3 is the challenging problem. All right. I have this many atoms of aluminum. Here's the density. What is the radius of my sphere if the aluminum is made into a perfect sphere? So I have that many atoms of aluminum. And in order to get a sphere, I need to have the volume to plug into the sphere. So to get a number of atoms into a volume, I need to know how many moles there were. Then I would need to know how many grams there were. And then using the density, I can figure out the volume of it, right? So that's what we're going to do to start. So in a mole, there are Avogadro's number of atoms. And we can turn moles of aluminum into grams of aluminum. And in a mole, there are 20-something, 26.982 grams of aluminum. And then finally, from grams of aluminum, we can do cubic centimeters using the density. So per cubic centimeter, there are 2.70 grams of aluminum. So how many cubic centimeters are there for my aluminum? 8.55 times 10 to the 22 times 26.982 divided by, parentheses, 6.022 times 10 to the 23 times 2.70. Close parentheses, enter. So the volume of my sphere in milliliters using these numbers is 1.42 cubic centimeters. Or milliliters. I think I said milliliters. That's okay. So I know that this equals the volume. And I also know that volume is, for a sphere, 4/3 pi r cubed. So if I wanted to solve for r here to find the radius of the sphere, that would be 3 times the volume over 4 divided by pi cubed root would equal r. And so that would be 3 times 1.42 cubic centimeters divided by 4 times pi. All of that cubed rooted, which would be, according to our calculator, so 3 times 1, oops, I don't know why I got a 9 there. 3 times 1.42 divided by, parentheses, 4 times pi. Do I have pi on here? I do. There's pi. So there's the innards of r square root. We're going to raise that to the power of 1 over 3. And you should get 0.697 centimeters for the radius of this sphere. Oh, gotta do the algebra right? If we're gonna screw up somewhere in this class, it's gonna be the algebra. All right, and then the last problem here. How many molecules of ibuprofen are in a 500 milligram sample? I'm going to do this just right off the bat so we can skip the milligrams to grams step because that's trivial. How many grams are there in a mole of ibuprofen? So C13, H18O2. So according to Lentech, it says 206.28. So that will tell us the number of moles we have. And then we'll do molecules. So moles of ibuprofen, molecules of ibuprofen. And in a mole of anything, Avogadro's number of that thing. So that should be molecules. My pen is freaking out here. All right, so calculator. 0.500 times Avogadro, 10 to the 23, divided by 206.28. And we get 1.459. Well, 1.460 times 10 to the 21. So that's how many molecules of ibuprofen there are in the sample. And if I want to find out how many carbon atoms there are, so I could say per molecule of ibuprofen, there are some number of atoms of carbon. So in each molecule of ibuprofen, there are 13 atoms of carbon, according to the chemical formula. So I just take my number and times it by 13. There you go. It looks like my answers matched up with everybody else's, so that's great. All right. Any questions, let me know. This, again, should all be review. I believe that's it for Chapter 2. Yeah, there we go. So there's our summary. So you can read through the summary if you'd like on your own. These are all the things that you'll be responsible for on the quiz. That quiz will go up online tonight. And then it will be due next Thursday with a closing time on Friday. So we have 5 minutes left. Let's introduce Chapter 6 here. So let me close this real quick so your screen will go blank before it lights back up. So we do skip over Chapters 3, 4, 5. Chapter 6 is not very long. We're going to finish this next week too. It is mostly review. Hey, look at these guys. Remember polyatomic ions? Now, it says on here you have to memorize the list of polyatomic ions. Guess what? Online class. Don't have to memorize anything. Ha ha ha. Suck it, Wes. Right? Now, it's in your interest to memorize the polyatomic ions, in my opinion. Particularly if you are a biology major. Because you're going to use tons of these. If you're an engineer, you probably don't need to memorize them, in my honest opinion. Here is the list of polyatomic ions from the OpenStax textbook that I have you referring to for this class. You'll notice that there are some that are not listed in the OpenStax textbook that I have put asterisks in. You should know these anyway. No meaning nowhere to refer to them, i.e. this slide. So I am going to refer to these. I am going to use these in examples. This is page 1. There is a page 2. The starred ones, again, not in your textbook, but I do expect that you know them, because if you know the chlorate series, you know the bromate series, and you also know the iodate series. They're all the same rules, So first few slides of Chapter 6 have your polyatomic ions. We are not going to use these until the end of Chapter 3, and that might not seem like it's very far away, but believe me, it is very far away. It's like 3 weeks away, so we'll come back to these later. It's not worth worrying about them for now, but I just want to mention that they're here. All right, what is Chapter 6? We're not actually going to balance chemical equations in this course. I'm going to leave that for Mark to give you in 162, or whoever your 162 instructor is. So this can just disappear. We're not going to do that. We are only going to do stuff from Chapter 6, which is basically simple empirical and molecular formula calculations. We did these in 160 or 140. And then we're going to do molarity and solution concentrations, which we also did in 140. So this is the back end of 140. Believe it or not, we have almost hit the point where we've done all of 140, and it's only week 3. So we have done a 10-week class in about 3.5 weeks, which is kind of the intent, because 140 is we take everything, we do it real slow, so you get lots of practice with it. So now you can do it real fast, right? All right. So the only thing I'm going to have time to talk about today is percent composition. What is the percent composition for any substance? It's this formula. The mass of whatever substance you are interested in divided by the total mass of the substance you're looking at times 100% is its percent composition. So let's do one example real quick. So I'm going to analyze a mineral, and I have determined that these are the masses that are in the mineral. Tell me the percent composition. So we'll go over here, and we'll do this example real quick just to end the lecture. We'll get rid of all this. Goodbye. So the percent composition of a substance, percent X, whatever X is the mass of X over the mass total times 100%. Well, let's figure out what the mass total is. So the mass total would be 15.9 plus, turn off exponential mode, you doof. 26.8 plus 17.4. I don't know why it's not hitting enter on my, there we go. So the mass total is 60.1. So if I wanted to do percent of iron in here, I need the mass of iron divided by the total mass, which would be 60.1 grams total. Now the grams cancel out. We're just going to ignore these units for now, because our target unit should be percent. So looks like this is roughly 25% iron. 26.5, that's close enough. And you can do the same thing for sulfur. So 26.8 grams of sulfur. Grams total, those are going to cancel, times 100%. Nothing is happening because I am not clicked on the calculator. Let's see here, 26.8 divided by 60.1. I lost a 1 here. I don't know where this went. There we go. So now I have, what, 44? Oh, I didn't times by 100. I didn't do that last time. I probably just read it as a decimal. So 44.6%. This was iron. This is sulfur. I've changed my pen settings somehow. I don't know what I did. Now everything is thick. Great, my pen is dummy thick. Just what I wanted. Whatever. I'm having so many Photoshop problems lately. Not sulfur. That I don't know what is even going on anymore. It's not grams of oxygen, it's grams total. $17.4, 60.1 times 100, 29%. There you go. I'm done. You're done. We're all done. So that's mass percentage. We're going to come back to more examples of that next week. All right. Thanks for coming out to the lecture. Apologize for all the technical issues I've had this week. Oops, that's the wrong button. There we go. Let's see here. So lab number 1 due tonight. Make sure you get that in by the deadline. I have about 20 or so minutes before I have to go do something. I have a game night that I am going to with friends, and I probably will not be back until like 10 or 11 or so. So if you ask me questions in the Discord, I won't get to them until then. That's kind of late for your lab, so don't ask last minute questions. Ask me anything you might have right now if you can. I'll try and answer it. Quiz number 1 is due tonight, but it closes tomorrow, so just make sure that you get that done by then, and you're all set. I'll go put quiz number 2 up after this, and that's it. Have a wonderful weekend. Thanks for coming to the lecture again. Get those assignments in, and we'll see you next week for Chapter 6. Take care.